Let's start illustration number 11. An inductor L and resistance R is parallel with an source or AC source of V volt. So L and R are connected parallelly to each other by voltage V. So such kind of arrangement first of all we see. So here is the arrangement of inductor L and R are connected parallel to each other and voltage V is applied to the circuit. We have to determine the total current I in terms of the inductance of reactance of L and the resistance R. And we have to also determine the phase difference. But first of all, we analyze the circuit. Here L and R, they are parallelly connected. And also the potential difference across them means between L and R is equal. So VL is equal to VR, and this result has been come from the law of parallel connection. Now you want to determine the phase difference, so we assume that the phasor of voltage is represented on x-axis. And with reference to the current phasor, we have to find out. But according to the characteristic, the phasor of current is given by this figure, in which you can clearly see the phasor of current in the inductor form and the resistance form are shown. So here VR is equal to VL, what we have already assumed. The current flowing through the resistor is in the same direction to the phasor of voltage V, and the current flowing through the inductor and the phasor of that current is pi by 2 difference with the voltage V. And now the phasor of IR is in the same direction to the phasor of VR. Now you see, up to the last theory, we have determined the direction of the phasor VR from the direction of the phasor IR. But here there is a reverse case has been placed, in which the phasor of IR has been determined from the direction of the phasor of VR. But the value of VR we know. What is it? It is IR into R. And so from this equation I can write down the value of current flowing through the resistor as IR is equal to VR over R. That is my equation number 1. Now if you again consider this figure, then according to the Pythagoras law, the magnitude of I is given by under root of IR square plus IL square. And now we have the value of IR. But what should be the value of IL? So it is VL upon XL. And the phase difference between the phasor of IL and VL, that is pi by 2. But actually it is minus pi by 2, because the phasor IL is represented on the negative y-axis. From this result, IL is equal to VL over XL, the total current or in proper you have to write it as the resultant current because there is absence of capacitors. So the resultant current is under root of IR square plus IL square, and the equation for voltage will be under root of 1 over R square plus 1 over XL square, and this equation you can directly determine by putting the value of IR and IL in this equation. So let's try the expansion from I to V. So here the value of I am taking it as it is under root of IR square. So what is the value of IR? So it is VR square over R square plus VL square over XL square. But we know the value of VR and VL are same. So I am taking it common by V. So it is inside 1 upon R square plus 1 upon XL square, and so the value of voltage V is equal to under root 1 upon R square plus 1 over XL square, and here not equal to. If V is equal to 1, if V is equal to 1 volt, then your I will be only 1 over R square plus 1 over XL square and is under root. So these are the equation for current I, and now the phase difference we have to find out. For that I am considering this equation of tan delta is equal to the vertical component. Here the vertical component is in the negative y-axis, which is IL and is divided by IR. Substitute the values of IL and IR, that is VL over XL into R over V, or in particular you can write down as VR. So the final value of tan delta is R over XL. Therefore, the phase difference delta between voltage V and current I phasor is tan inverse R over XL. And with this, illustration 11 is also over. Now let's switch on to illustration number 12. Illustration number 12. Derive the expression for total current flowing in the LCR parallel circuit using the phasor diagram. So this is the LCR parallel circuit which you can see from the figure, and voltage V is applied to the circuit, and we have to find out the total current. Here all the components what you are watching are parallel to each other, and so the total voltage which is passing through this is the combination of the potential difference at the ends of each and every component. But it is necessary that we should find out the phasor diagram, because here it is written that we have to use the phasor diagram for the determination of total electric current. So here is the phasor diagram in which we have taken voltage V or the phasor of V in the x-axis, and the phasor of current in resistance R is also on x-axis. So the phase difference between V and IR, so delta is equal to 0, and here IC means the phasor of electric current in the conductor is on positive y-axis, and the phasor of electric current in the inductor side is on negative y-axis. the phase difference between voltage V and the phasor vector which we have determined using the combination of inductor and capacitor IL minus IC, that is also in the negative y axis. So now with the help of this, if we apply the Pythagoras theorem to this much triangle, suppose it is the triangle AOB, then or OAB triangle, then by using the Pythagoras law, this AB value is IL minus IC. This OA value is IR. And suppose I consider that the total current flowing through the circuit is capital I, then from triangle OAB, the value of electric current I is equal to IR square, and here square is also come because it is a Pythagoras law. IR square plus the another term is IL minus IC whole square. And so if I take under root of this, so the value of I is under root IR square plus IL minus IC whole square. We know the value of IR according to Ohm's law, that is given by V over R. The value of current passing through the inductor is given with respect to voltage and reactance of the inductor, so it is V upon XL. Also the value of current passing through the capacitor is given in the similar way of inductor, so it is V over XC. Now substitute all these value in the equation of I. So I is equal to under root of V square over R square plus V over XL minus V over XC whole square. But here V square will come out of the second term. So it is V square over R square plus V square into 1 over XL minus 1 over XC whole square. And now taking V square common and outside the square root, this V square will become only V. Therefore, I is equal to V under root of 1 over R square plus 1 over XL minus 1 over XC whole square. So this is the value of electric current, and from this figure we have the value of tan delta as vertical arm. The vertical arm is IL minus IC and the horizontal arm was I into R. So here substituting all the values, VL over XL minus VL over XC divided by V over R. And here instead of writing VL, it is better we should write VC. But the voltage flowing through all the circuit components, this VL is equal to VC is equal to V. So cancelling V from all the sides, so the answer will be 1 over XL minus 1 over XC divided by R. So this denominator of denominator will now come into the numerator. It is actually 1 over R. Therefore, I is equal to, here tan delta will come, because we are going to find out the phase difference. So tan delta is equal to R into 1 over XL minus 1 over XC, and therefore the phase difference delta is equal to tan inverse into R into 1 over XL minus 1 over XC. So this is the phase difference, and now we will see the different type of flow of current. Here we have seen that the current is flowing linearly. But what happened when the current is oscillating? By changing the value of this inductor and capacitor. So that is our next task.